This is the last part of Unit 3, Household Electricity and Magnetism, and this is podcast 4, Electromagnetic Induction. Okay, electromagnetic induction is a process by which you make electricity. And to create a current, all you need is a changing magnetic field and a conductor. So you have to have your magnetic field changing, and I'll explain all the ways that you can change your magnetic field, have some kind of change going on. This process is called electromagnetic induction. And you do need to know the proper name of that because it's very often asked for 1 mark in an exam. So, how do you get a changing magnetic field? Well, the easiest way to get a changing magnetic field is to move a magnet. And if you move a magnet into a coil of wire, which is just connected to a little meter, you'll find that your needle of your meter goes one way and back to 0. And then when you pull it out again, it goes the other way and back to 0. Now you should always finish your sentence with and back to 0, because if you just say it, when you move your magnet in, it goes one way, then the examiner thinks that you think that it goes one way and stays there. It always goes back to 0. There has to be a change going on. And the change that's going on as you move that in is that we imagine that those coils of wire are cutting the magnetic field around that magnet. If I just draw the magnetic field around that magnet just a minute. So you've got your loops at each side, something like that, the top and the bottom. And if you can imagine putting that in there, these lines here are cutting that magnetic field, and that's a change in the magnetic field. But that induced current only happens whenever the magnet is moving or the field lines are being cut, and that's a change. So you only get this in current induced when there is a change. So when you move it in, it goes one way and back to 0, and when you do the opposite thing, move it out, it goes the other way and back to 0. So that's moving a magnet. Could you induce current by moving the coil or a wire instead? Of course you could. You could move your conductor into the magnet, into the magnetic field, and cut the field lines, and you would have your current in just one direction and back to 0, and then pull your coil out again and just the other way and back to 0. So we actually have got current induced in these coils of wire, and it flows first of all one way when you move it in, and then it switches around and flows the other way whenever you move it out again. The same idea is true if you move a conductor. So if you move your wire up or down through this magnetic field, and you had a voltmeter or an ammeter connected here, I'll just connect this circuit, then you will have current, if you move it up, flowing one direction, but then when you move it down, your current will flow in the other direction. And again, that's very easy to think about, you cutting the magnetic field lines there, cutting up and down through them. Okay, so you know already that you can move a magnet or move a conductor in a magnetic field, but you could also move an electromagnet. So electromagnet is really just a magnet as well. You make an electromagnet by using a power supply, which you can switch on and off possibly, which you could increase the current of, and you have a magnetic field surrounding this. So if I maybe just even draw that in, there's your line and there's your loops, top and bottom. And again, you could move your electromagnet into this second coil of wire sitting beside it, and you would have your current just in one direction and back to 0. And then if you pull your magnet out, your electromagnet out, then it moves the other way and back to 0. So you get current flowing in this coil in one direction and then in the opposite direction when you make the opposite change. So really this electromagnet is really just behaving like your little bar magnet. Now, we said it was a change in the magnetic field. You don't even need movement. All you need to do is to get it to change. So there's our electromagnet again and our second coil of wire. If you close that switch, you have a magnetic field which grows around your electromagnet here. So that's a change, and that change is enough to cause a flick in your ammeter and back to 0. if you open it again, now lots of people think when you open it again that's at nothing on this meter. In fact, what you're doing is that this magnetic field is shrinking away to nothing. And when it shrinks away to nothing, that's a change. That induces a current over here, and it flicks the opposite direction and back to 0. So whenever all you need is a change, that's all you need. So that you imagine that field growing and then going away again, and that's just the change that you need to induce current in your second coil which is nearby. Another way of doing it is by increasing or decreasing the strength of an electromagnet. Now this particular diagram that I got has actually got an iron bar between it, and an iron bar will really intensify this effect. It really helps. So all you need to do here again, if you increase the strength of the electromagnet or decrease it by using a variable resistor in the circuit. And when you have your variable resistor and increase this, you get far more field lines. So if you've got a low current through here, you may have, I'll just draw one loop at the top, but I'll leave plenty of room so I could draw another one. You might have a pattern like that. But if you increase the current through here, then you've got far more field lines in between, and they're far closer together, and so on. And when you do that, you are making a change. So a change in the magnetic field, you induce current in one direction, back to 0. Then whenever you reduce the current here, the field is much weaker, then that's the opposite change, so flicks in the other direction and back to 0. If you put soft iron between them, it intensifies the whole effect, because iron is a magnetic field, magnetic material, and it increases the strength of the magnetic field. Another thing that you can do is, instead of using a DC, and I'm sorry I've still got a DC diagram in here, you could use AC. So if I just score that out there, and instead, in fact I'll just use black so that you're not confused. Okay, instead we say that we have got an AC supply here. Now, an AC supply is a supply which is continually changing direction. So what we imagine happens here is that whenever you switch this on, you've got a magnetic field around this electromagnet, but it continually changes direction. So if you're using your right hand rule, you might be putting your hand down like that and saying this is the North Pole, but when it changes direction, this is the North Pole. North Pole, North Pole, North Pole, North Pole. And so what you're doing there is changing the direction of the magnetic field all around. It's continual. So what you'll have over here is this change continually going on, plus, minus, plus, minus, plus, minus, plus, minus, and so on. Whatever frequency this is operating at, say it's 10 Hertz, then this induces current at the same frequency. So if this changes direction 10 times a second, so does this. Now this is a typical kind of question that you might get on electromagnetic induction. And you can see here it says a person moves the magnet into a coil and leaves it there. When does a current flow in the coil? So you know it's only when the change is happening. So you know that it's whenever this magnet is moving, the coil's cutting the magnetic field around the outside of the magnet, and that's when the change is happening. So when does the current flow in the coil? The current is going to flow one way and back to 0 when the magnet is moved in, and then when it's pulled out again, it's going to flow the other way and back to 0. Now, you're not asked that. You're only asked a person moves a magnet into a coil and leaves it there. So the current is only flowing when the change in the magnetic field is happening, and that's only happening when the magnet is moving. The diagram below shows a magnet attached to a spring. The coil is connected to a sensitive ammeter with a centre 0 scale. That just means that the pointer's in the centre. Describe what is seen on the ammeter when the magnet is made to move in and out of the coil. So again, there's this movement idea happening. We'll assume that it's moving up and down on the spring. So that's a continual movement. So as it moves in, you're going to get your needle pointing one way and back to 0. And as it moves out again, the opposite effect is going to point the other way and back to 0.